Welcome to part 10 of the tutorials for the PIC16F171 chip family. Let's get straight into it. Today we're looking at using the CCP PWM module within this chip to actually control the brightness of the LEDs. What I'm using in terms of the hardware, I'm using exactly the same as I've used in the previous videos, the microchip low pin count demonstration board. And as previous, we've provided a layout that you can make with a breadboard of the same layout. So what I've got today, though, is some new hardware. I'll show you this hardware very briefly, and then we'll look at the real one. I've got a little small oscilloscope, so I've got a common ground between the two devices, and I'm measuring port C.0 into one of the inputs of the oscilloscope. Let's have a look at the actual hardware I'm using. Here it is. The green is the PCB of the low pin count demo board, the chip itself, and here is the oscilloscope. And you can see two connections. And at the moment, there is no signal from the chip, and therefore on the screen on the bottom right hand, there's a PC representation of the oscilloscope. And we'll see that change as we progress. Turn the video off. So what is pulse width modulation? It's simply a succession of pulses, and it's a method of reducing the power in the electrical signal by chopping it up into discrete parts. That gives you an average voltage fed to the load, and our load is the LEDs, by turning it on and off at a fast rate. The longer the signal is on compared to the off periods, the higher the power that is supplied to that load. It's a very simple and common practice. So our goal is to control the LEDs. Clearly the LEDs are connected on that board via suitable resistors, but we're going to be using a fixed frequency. I've chosen a particular frequency. You can play with that frequency to see the impact. And we're going to change the duty cycle by reading the ADC, which we've done in the previous tutorials. And how do we do that? It's relatively simple. We're going to read the ADC value. Let me bring my pen up on the screen here. Pointer, ballpoint pen. We're going to read the ADC. Then we're going to scale that just to make sure that we get it in within the range that we require. And then I'm going to use a command called HPWM, hardware PMW. Great Cow BASIC also supports software pulse width modulation. Therefore, I just need to make sure I'm using the right one. I'm going to do it on channel 1. I've chosen a frequency. It says 20 on the screen. I think I'm using 5. You can change that and play with that with your heart's content, but have some fun with it once you get into the demonstrations. And then I'm setting the duty cycle, but by passing it the parameter or the variable called ADC value. Let's just erase things on there. So it's this one command. And so we need to pass it the CCP channel, the frequency, and the duty cycle. And with that, we have pulse width modulation. So what we're going to do is examine the sample code. We're going to have to set up the CCP PMW using PPS. We have seen this before, but I'll recap that. And then we're going to read the ADC value to set the duty. Let's review the results. So let's go to my desktop. And you're going to see some different things, because that's the PC screen for the oscilloscope. But let me just press Windows, GCStudio, and it will bring up GCStudio. Let me zoom in and take the demonstrations that we've been choosing before, and it will take us into GC code. And here we are, GC code. Now, we've been doing this. I'll repeat it again. Click on the files. Let's just filter out all the things we're not interested in, all the other files. And we need to open up. Use 120. Use PMW via CCP and ADC. And here we go. Now I'm going to close down the Explorer. Great. We're in the program. Exactly the same as before. Hash chip, 16F17126, option explicit. And then we've got the PPX section. Let me just minimize that. Because where does this come from? All this, where does this come from? It comes from the PPS setup. You can refer to the datasheet or you can use PPS tool. Press F4, PPS tool, and open it up. Let me just zoom in on the PPS tool. It's currently loading a list of the files. I haven't loaded this morning. And I'm now going to select the chip I'm using. (16F17126). This CCP, pulse width modulation, or PWM, is actually called CCP1. You'll see it listed here. There's two of them, CCP1 and 2 on this particular chip. I just want to use one of them, so I click on it, and then I'm going to set the outputs of that on my 4 LEDs by selecting RC0 and adding, RC1 and adding, RC2 and adding, RC3 and adding. Now I've got a list of configurations which I can copy and then go back into my program. And then just to prove it's all working, I'm going to delete the whole section. Have I deleted the whole section? Nope. Here we go. Delete it. And then I'm going to paste that back in. No, I'm not, because I've done that wrong. So let's just recreate that. Don't do things live. That's what they say. I'll show you what I'm doing. I'm just recreating what I messed up. Copy. Back into the editor and paste it in. And it is a complete program. It has a hash startup to call the initialization process. It has the subroutine with all the parameters set up for you. And that is the PPS setup. It is connected CCP1 PMW to all of the 4 ports that we selected. We have our 4 LEDs on our little diagram, and then we have the same constants as before. Very similar program to what we've seen before. There's a do loop forever. It reads the ADC value and puts it into a variable, a byte variable called ADC value. I scale that value because the maximum I'm getting from this particular board is a value of about 4.3 volts. That's because of the resistors. So I'm just going to scale that up to between 0 and 213 is what I read. We saw that on the serial output on the previous tutorial. I'm scaling that to 255. I'm waiting for 10 milliseconds, and then I'm using the method HPWM, and I'm saying use CCP1, which is on PMW1, a unit of 5. And if we look at that, we can look at the units here. They're always integers. I press F1. It will bring up the help, and it's always a frequency. So the parameters are channel, frequency, and duty cycle. And I'm simply setting the duty cycle to ADC value. If I program that and go to the scope, we can see what happens. It's now programming it. We can now see on the oscilloscope a square wave. That square wave, according to what I can see here, is about 50%. I'm connecting my screwdriver here, and as I rotate the screwdriver, the square wave changes and the LEDs get brighter. Let's go full off or dimmer. So what we're doing is reading in the ADC value, setting the duty cycle without changing the frequency. We can get it to go off. So I think we'll go full on, nearly full on. There we go. Very simple. One command. Let's go back to the code. But it is one of my favorite demonstrations. I love the way it does that. So it's as simple as read the ADC value, scale it to something that's meaningful. I do wait 10 milliseconds. I don't like hammering the particular module, and then passing it the three parameters of the channel I've selected, which was CCP1 inside of PPS tool, because there's only two on this particular chip. There is CCP1, CCP2. You could have them at different duties. They do use the same timer, so you can have different duties, but not different frequencies. We'll come into that later on in a later tutorial. I set it to 5 as the frequency, and then the ADC value. And that's it. It's a very simple program. So that's it for today. What we wanted to do was set up the CCP pulse width modulations to control the brightness of the LED. Job done. Tomorrow we're going to look at using the I2C over serial so that we can discover I2C devices. So we're going to take away the little oscilloscope and put in an I2C device. We're going to do some discovery and make that happen. And with that, we'll call it a wrap.